Okay, so I'm doing this short video for the solution of the assignment 4. So basically we did the analytical solution for the first problem, which is this one over here. And this is basically what we found for this problem, okay? Summarizing, this is the simplified sketch. In order to find the forces, we do the position vectors, assuming this is the origin of our reference frame. Then to do the moments, we just do R cross F, and this gives us the loading, okay? So I think I define, okay, so this will be the loading as shown over here. We define these cross-section properties given by this, the area, the i's in the circular, the ix, iy will be the same, and then the j is only half of it. The Q over here, since it's circular, is basically the same. All right. All right, so this is the area times the y, which is a distance to the point we want to do it. So stresses at point 8, okay. We found, I mean, we went in detail in class, so y here is 0 because we are located over here, point A, so the y distance is 0, okay? So that's why the moment, the normal stress created by the mx moment is equal to 0, and only the moment about the y times the x, which is y around this axis times x, create normal stresses. And we found that to be equal to 47.7465. Then doing the shear stresses, basically first due to the Fx force going in that direction. Since point A is at one of the tip, there is no surface to rub, so the Q sub A is 0, so the shear is 0. And then for the Vy, this time you see you have all this area here. Oops, which one is this one? Okay, you have all this area here, or you actually, oh, it's point A is here, so this should be the area over here. Okay, so selecting that area, and then the y bar will be the CG for the semicircle, which is given by 4r over 3 pi. I provided that information with the problem statement. And if you do this, you get 1.061. Then the moment about Z over here, okay, we create no shear, we create shear, but due to the torque. And we have here that the shear due to the torque is equal to 47.7465 as well, which is going on the same direction as this one. So we were able to add them together. All right. So the reason I'm doing a video is that we cannot check these values, but we can check this value here with the final element with FEMAP. So what I did is I came over here. All right, let me move this, but basically the origin would be at point A here, okay, at the cut. And I will create 1 point here, 1 point here, 1 point here. All right, so here we go, geometry points. So it will be 0, 0. Then instead of using the Z, I'm going to use the Y. This should be 200. And then for the Y will be our X. So 0, 200, 400. Okay, cancel, Control A. So now we can go to geometry, curve line, points, methods on point. We click here, or enter, click here, enter, click here, enter, click here, enter. So this is basically this part of the beam, okay? Now we need to apply the loads at the tip. So let's say, oh, not yet. So first let's mesh. So we don't really use the material, but in order to run, we need to define a material. So I know this is still in millimeters, this would be 207, it would be 0.3, but you can put any value here because we are not calculating deformations. Okay. Cancel properties, new. We select that material. For this simple problem, we're going to use the beam property. Okay. And from the problem statement, we know that the radius of the cross-section is 20 millimeters. So what we can do is here shape. We use a bar, radius 20 millimeters. I'm going to make sure this is here. And I think we need to calculate the stresses at 0.4. But let's keep just 2 and 4 if you want, in case it doesn't do what we want. Okay, let's go over here again. So if you see point A here, all right, it would be right here along the X. And if I put here, this is the Y, this will be the 0.2 or 0.4. I think it would be 0.4, but we can figure that out later on. Okay, so I give us all the properties that we calculated, so we should get the same values. Okay. Now we do mesh control size along curve. I select the 2 curves, and let's do something pretty small. Let's put element size 4. Okay, so you see that's pretty refined. Now we go to mesh geometry curve. Here, be careful. We're going to do one at a time because we need to pay attention to the orientation of the cross section. So if you remember, here is we sit on the Y. So we keep it on the Y. It's not going to work because just be showing that it would basically go in that direction. So what I need to do is on the X or the Z. Here's already the X. So you see preview. Okay, so if you want to check over here, something you can do is come over here. Just thickness orientation, you see it did the right thing. Mesh geometry curve can come over here. And this time the direction of the orientation should be on the Y. So we're going to have to change this. 0 to Y. Okay. All right. So we see this is done properly. Now we can eliminate this. And model constraint nodal. We know it's fixed. We can go here. Okay. Fix. All right. Cancel. Then model load nodal. We go to this one at the tip. And we know we have what? Let's see. 1 in the axial direction of 1000. So that would be, axial direction would be the X of 1000. Okay. And then the other one is in the opposite direction, 1500. So let's say we'll be on the negative Z. Oops, over here. Minus 1500. All right, cancel. So let's see, we look at it. You see it's that way. F8, XY top. All right. So, since we mesh this in different times, probably the mesh over here, the corner should be common to both of them. So what we can do is tools, check, coincident nodes, select all, okay, preview, and you see this one is redundant. So what we do is we're going to merge those 2 nodes. Okay. So we go file, save as over here. Whatever we can do here, I can call it here temp. Save. And now go here, you can click over here, create any new set, new, make sure it's static. Okay, analyze. It should be done very quick. All right, we can go look here at the results. So we click F5, beam diagram, probably that's what we should do. You can put that or not, but here this is probably just going to give you the combined stresses. So I think it was combined stresses 0.4. I think that's the one we need to check. But if we find out now, so you see this will give you the distribution for all of them. Upward. So it might be B actually, but we'll find out now. From the solution, okay, we found 47.7465 in tension. So I think, all right, let's select this one as a group. So let's go here to groups, new. Let's say at cut or at the base. Okay, groups, element ID. You select the first element. Okay, you go here to groups, open it, select show active group. And you see he's giving you this intention. So we needed to look at the other one, which is F5, deform. So basically 0.2 combined stresses. And now you see, so the analytic, this solution, it will give you about 47.75. The change, you see, just because of the mesh size, but you need to look at the highest one, which would be the bottom, is a 47.75. And in the classic solution we had 47.7465. All right, so that's all.